Imagine standing at the top of the world, where the land stretches out flat and pale and endless in every direction. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. The sky above you is enormous. It goes on forever. A cold silver dome pressing down on a frozen earth. The wind moves across the ground in long, slow waves, bending the low grasses like the surface of a quiet sea. There are no trees here. There are no tall things at all. Just the open land, the open sky, and a silence so deep you can feel it in your chest. This is the tundra. The word itself comes from a Finnish word, tunturi, which means a treeless plain. And that is exactly what it is. A vast, open, wind-swept land where the cold is not a visitor. The cold is the permanent resident. It has lived here for thousands of years, and it has shaped every single thing you see. The tundra covers roughly 10% of Earth's entire land surface. That is an almost impossible number to picture. Think of all the land on Earth, every continent, every country, every mountain range and valley and desert. Now take a tenth of all of that and paint it white and brown and gold. That is the tundra. It wraps around the top of the planet like a wide, pale crown, stretching across northern Canada, Alaska, Russia, Scandinavia, and the edges of Greenland. From space, it looks like a border. A ring of pale earth sitting between the dark green forests to the south and the white ice sheets to the north. Astronauts looking down at Earth have described this band of land as one of the most striking features on the planet's surface. It is a clear line where the world changes, where the trees stop, where the rules of life become different, and those rules are strict. The average temperature in the tundra sits well below freezing for most of the year. In the deepest winter months, temperatures can drop to negative 30 or 40 degrees Celsius. That is cold enough to freeze exposed skin in minutes. Cold enough to crack rock. Cold enough to keep the ground itself frozen solid, not just on the surface, but deep down, sometimes hundreds of meters below your feet. Scientists call this permafrost, ground that stays frozen all year round, year after year, century after century. But here is the thing that makes the tundra so astonishing. Life is here anyway, not in spite of the cold, not struggling against it. Life here has learned to work with it, to fit inside it, to find every small gap where warmth and light exist and use it completely. The tundra is not empty. It only looks that way from a distance. Up close, it is full of motion and color and quiet, patient survival. In the brief summer months, the sun barely sets. It circles low along the horizon for weeks at a time, casting long golden light across the land for 20 or even 24 hours a day. The ground thaws just a few centimeters at the surface, and in that thin sliver of soft earth, under that low golden sun, something remarkable happens. Flowers bloom, insects hum, birds arrive by the millions. The whole landscape shifts from pale and still to vivid and alive almost overnight. Then winter returns, and the tundra goes quiet again. This rhythm, this long, slow breath of freeze and thaw, has been going on for a very long time. The tundra as we know it today began forming after the last great ice age, roughly 10,000 years ago, when massive glaciers retreated and left behind scraped, bare land. What grew back was not forest. The soil was too thin, the cold too persistent. What grew back was the tundra, low, tough, patient, and enduring. It is one of the youngest major ecosystems on Earth, and yet it feels ancient. Standing in it, you feel the weight of deep time, the slow grind of ice, the long darkness of polar winter, the return of light, over and over and over again. Tonight, we are going to spend time in this remarkable place. We will learn how it works, what lives here, what hides beneath its frozen surface, and why this cold and quiet land matters to every single living thing on Earth. So settle in. Close your eyes if you like. Let the tundra come to you, slow and still and full of wonder. The tundra covers more of our planet than most people ever think about. It wraps around the top of the world like a wide, frozen crown. From Alaska to Canada, across Greenland, through Scandinavia, and all the way across northern Russia, the tundra stretches in an almost unbroken ring around the Arctic. Scientists call this the Arctic tundra, and it covers roughly 5.5 million square miles of Earth's surface. That is nearly twice the size of the entire United States. It is a vast, open world. But the Arctic is not the only place where tundra exists. High up on mountains, above the tree line where trees can no longer survive the cold and wind, you find a different kind of tundra. Scientists call this alpine tundra. It sits on the shoulders of great mountain ranges all over the world, from the Rockies in North America to the Andes in South America to the Himalayas in Asia. Even mountains near the equator can carry tundra on their highest peaks, where the air is thin and the cold is fierce. The tundra does not belong only to the poles. It belongs to the heights as well. There is also a third kind, smaller and less known. Antarctic tundra exists on the edges of Antarctica and on a few scattered islands in the Southern Ocean. These are cold, windswept places where only the hardiest life clings on. Together, all three types of tundra cover about 10% of Earth's total land surface. 1 out of every 10 square miles of dry land on this planet is tundra. To understand where the Arctic tundra sits, think of it this way. Imagine drawing a line around the top of a globe, circling the North Pole. That line, which scientists call the Arctic Circle, marks roughly where the tundra begins. Below that line, conditions are warm enough for forests to grow. Above it, the cold winds. The tundra begins where the trees give up. The southern edge of the Arctic tundra meets a great belt of forest called the boreal forest, or taiga. Taiga is the Russian word for this dense, cold woodland of spruce and pine and fir. The line where tundra ends and taiga begins is called the tree line. It is not a sharp line you could walk along in a single afternoon. It is a gradual shift, a slow fading. Trees grow shorter and more scattered. Then they disappear, and the open tundra begins. That tree line is one of the most important boundaries in nature. On one side, a forest. On the other, a wide open plain of low plants and frozen ground. The difference between the two sides can feel dramatic, like crossing from one world into another. But the shift happens over miles, quietly, the way most great changes in nature do. The Arctic tundra sits between roughly 60 and 75 degrees north latitude. To picture that, think of the city of Anchorage in Alaska, which sits at about 61 degrees north. The tundra begins not far from there and stretches all the way up to the edges of the Arctic Ocean. In Russia, the tundra zone runs for thousands of miles from west to east, covering more land than any other single country on Earth contains in total. The average temperature in the Arctic tundra during winter drops to around -20 to -30 degrees Fahrenheit. That is cold enough to freeze exposed skin in minutes. In summer, temperatures rise, but only to around 35 to 50 degrees Fahrenheit on average. That is not much warmer than a cool autumn day in many parts of the world. The growing season, the window of time when plants can actually grow, lasts only about 50 to 60 days each year, less than 2 months. Plants must do everything they need to do, grow, flower, and seed, in that narrow slice of warmth. Precipitation in the tundra is surprisingly low. Most of the Arctic tundra receives less than 10 inches of rain and snow per year. That is less than many deserts receive. The tundra is, in a technical sense, a cold desert. The difference is that the cold traps what little moisture falls. It cannot drain away or evaporate quickly. So the land stays wet and boggy in summer, even though very little new water arrives. This combination of extreme cold, short summers, low rainfall, and frozen ground creates a place unlike anywhere else on Earth. It is not a place that welcomes life easily, and yet life is here, quietly, stubbornly, beautifully, waiting for its moment, finding ways to survive in conditions that would stop most living things cold. To understand why the tundra is the way it is, you have to understand light. Not just the presence of it, but the absence of it. The way it comes and goes in this part of the world is unlike anything most of us will ever experience. And that rhythm of light and dark, more than almost anything else, is what made the tundra what it is today. The Earth tilts on its axis. That tilt is about 23.5 degrees, and it never changes. As the Earth travels around the sun each year, that tilt means means different parts of the planet lean toward the sun at different times. In summer, the high northern latitudes lean in close. In winter, they lean away. For most of us, this just means longer days in summer and shorter days in winter. But near the poles, the effect is extreme. It becomes something else entirely. In the Arctic tundra, winter does not just bring cold and short days. It brings darkness, real, total, weeks-long darkness. For communities north of the Arctic Circle, the sun does not rise at all for a stretch of winter. This period is called polar night. In some places, it lasts for 2 months. In others, closer to the pole, it can last nearly 4. The sky stays a deep, bruised blue or black for weeks on end. Stars appear in the middle of what should be afternoon. The land grows still and quiet under that long, unbroken dark. During polar night, temperatures drop fast. With no sunlight to warm the ground, the cold settles in deeply. The snow hardens. The ground, already frozen, locks tighter. The wind moves across the open plain without anything to slow it down. There are no tall trees to break the gusts. The tundra in winter is one of the most exposed places on Earth. The cold is not just a number on a thermometer. It is a physical presence. It presses in from every direction. Then something shifts. Slowly, almost imperceptibly at first, the sun begins to return. It appears on the horizon for just a few minutes. Then, a little longer the next day. The light is low and golden, skimming across the snow at a shallow angle. It turns the white plain pink and amber. It is one of the quieter wonders of this planet. That first sliver of returning sun after weeks of darkness. And then summer arrives, and everything reverses, because the same tilt that hides the sun in winter brings it back with full force in summer. Above the Arctic Circle, the sun does not set for weeks. This is called the midnight sun. The sky stays bright all through the night. At 2 in the morning, the light looks like late afternoon. The sun circles the horizon in a slow, low loop, never dipping below it. For someone who has never experienced it, it is deeply strange. The body does not know when to sleep. The birds sing at midnight. The ground, freed from darkness, begins to warm. This extreme swing between polar night and midnight sun is not just a curiosity. It is the engine that drives the tundra's entire existence. The long winter darkness is why the ground stays frozen so deep. The brief, blazing summer light is why plants can bloom at all. Life in the tundra evolved around this rhythm. Every living thing here, every plant, every insect, every bird that visits, has its internal clock set to this strange and powerful cycle of light. The tundra did not form overnight. It took thousands of years of this pattern, repeated over and over, to shape the land into what it is. After the last great ice age ended, roughly 10,000 years ago, glaciers retreated northward. They left behind scraped, bare ground. Slowly, over centuries, the first simple plants moved in. Mosses and lichens came first, as they always do. They began the slow work of building soil from bare rock and mineral dust. The tundra, as we know it, grew from that patient beginning. The tilt of the earth created the darkness. The darkness created the cold. The cold created the frozen ground. And the frozen ground, combined with those brief, sun-drenched summers, created the conditions for a very particular kind of life to take hold. Everything here traces back to that original angle, that 23.5 degrees of lean that sets the whole cycle in motion. It is a quiet kind of origin story. No volcanoes, no collisions, no dramatic explosions. Just the slow, steady turning of a tilted planet around its star, year after year, for thousands of years, gradually shaping one of the most remarkable places on Earth. Look up on a clear tundra night, and the sky does something extraordinary. It fills with color. Pale green ribbons ripple across the darkness, sometimes pink, sometimes violet, sometimes a deep and ghostly white. This is the aurora borealis, the northern lights, and it is one of the most beautiful things our planet produces. It happens because of something happening far above the ground and far out in space, all at once. The sun is not quiet. It constantly sends out a stream of tiny charged particles, electrons and protons, moving at enormous speed. This stream is called the solar wind. When those particles reach Earth, our planet's magnetic field, The invisible force that wraps around the globe like a protective shell catches them. Near the poles, the magnetic field dips closer to the surface. That is where the particles slip through. They collide with gases high in the atmosphere, and those collisions release light. Green comes from oxygen about 60 miles up. Red comes from oxygen even higher, over 100 miles up. Blue and purple come from nitrogen. The tundra sits directly beneath one of the best windows on Earth for watching this happen. The atmosphere above the tundra is the same air that covers the whole planet, but the cold shapes it in particular ways. The air here is very dry. Cold air holds less water vapor than warm air does, so the tundra sky is often startlingly clear. Stars appear sharp and close. The Milky Way, that broad pale band of hundreds of billions of distant suns, stretches from horizon to horizon on a dark winter night. The light reaching your eyes from some of those stars left its source thousands of years ago, long before the first human ever walked across the tundra ice. That connection between the sky and the ground runs deeper than just light. The oxygen in every breath of tundra air was made by living things, mostly ancient plants and ocean algae, over billions of years. Before life existed, Earth's atmosphere had almost no free oxygen at all. It was mostly nitrogen and carbon dioxide. Tiny ocean organisms called cyanobacteria began releasing oxygen as a byproduct of using sunlight for energy. Over an enormous stretch of time, that oxygen built up. The air we breathe today, roughly 21% oxygen, is a gift from billions of years of living things doing their quiet work. The nitrogen that makes up most of the air, about 78% of every breath, has its own ancient story. Nitrogen is one of the most common elements in the universe. It was forged inside stars in the tremendous heat and pressure of stellar cores, long before our solar system existed. When those stars died and scattered their contents outward, nitrogen drifted through space. It became part of the cloud of gas and dust that eventually collapsed to form our sun and its planets. The nitrogen in the tundra air today has been cycling through Earth's atmosphere, oceans, soil, and living creatures for billions of years. It has been part of countless organisms before it reached this cold and open sky. The carbon dioxide in that same air matters enormously to the tundra. Plants, even the small and simple ones that grow here, pull carbon dioxide out of the air and use it to build their bodies. When those plants die and fall into the cold, wet ground, they do not fully decay. The frozen soil slows the process almost to a stop. Carbon that was once in the air gets locked into the ground. The tundra has been doing this for thousands of years, storing carbon in its frozen soil like a vast, cold library. Scientists estimate that the tundra holds more carbon in its soil than is currently in the entire atmosphere above it. Water vapor, even in small amounts, plays its role too. On the coldest and clearest nights, ice crystals form high in the atmosphere and catch the moonlight. They create faint halos around the moon, soft rings of pale white, and sometimes faint color. These are called lunar halos, and they appear often over the tundra in winter. They are caused by light bending as it passes through millions of tiny six-sided ice crystals, each one a perfect geometric shape, drifting slowly through the dark air. Every element in that cold sky, the oxygen, the nitrogen, the carbon, the water, the charged particles streaming in from the sun, has traveled an almost unimaginable distance to arrive here. Some of it was forged in stars that burned out before our planet existed. Some of it arrived on icy comets billions of years ago. All of it came together, slowly and precisely, to fill the sky above this frozen plain with color and cold and quiet light. Beneath that sky, beneath the cold light and the drifting ice crystals, the ground holds its own quiet secrets. The tundra is not just frozen on the surface. It is frozen deep down in layers that have not thawed in thousands of years. This frozen ground has a name. It is called Permafrost, and it is one of the most powerful forces shaping the tundra world. Permafrost is simply ground that stays frozen for at least 2 years in a row. But in the tundra, it does not stay frozen for just 2 years. It stays frozen for hundreds of years, sometimes thousands. In parts of Siberia, the permafrost reaches down more than a mile into the earth. scientists have drilled into it and found ice that formed during the last great ice age, long before humans built their first cities. That ice has been locked in place ever since. The permafrost does not sit right at the surface. Above it, there is a thin layer of ground that does thaw each summer. This upper layer is called the active layer. It might be only a few inches deep in the coldest parts of the Arctic. In slightly warmer areas, it can reach down a few feet. Each spring, the sun returns and warms this thin layer. Plants grow in it. Water pools on top of it. Animals dig into it. Then winter comes again, and it freezes solid once more. The active layer breathes in and out with the seasons, while the permafrost below it never moves at all. This freezing and thawing creates enormous pressure inside the ground. Water is unusual among the materials on Earth because it expands when it freezes. Most things shrink when they get cold. Water does the opposite. When water trapped in the soil turns to ice, it pushes outward in every direction. It shoves rocks aside. It lifts the ground upward. It cracks the surface into strange and beautiful patterns. Over many years, this slow, relentless pushing sorts the soil and stones into shapes that look almost designed. Circles of stones appear on flat ground. Polygons form across wide plains, their edges raised like the walls of tiny rooms. These patterns are called patterned ground, and they stretch across enormous areas of the Arctic. From above, the tundra looks like it has been tiled by a careful hand. One of the most striking things the frozen ground builds is called a pingo. A pingo is a hill made almost entirely of ice, covered by a thin skin of soil and grass. It forms when water underground freezes and expands, pushing the ground above it upward into a dome. Some pingos grow slowly over hundreds of years, rising a few inches each decade. The largest ones can reach over 200 feet tall and stretch more than half a mile across. They rise from flat plains like smooth, rounded islands. From a distance, they look like gentle hills, but inside, they are solid ice. There are thousands of pingos scattered across the Arctic, most of them in northern Canada and Siberia. The frozen ground also traps water in ways that shape the whole surface of the tundra. tundra because the permafrost is solid and impermeable, meaning water cannot pass through it. Rainwater and snowmelt have nowhere to drain. The water sits on top of the frozen layer, spreading out across the land. This is why the tundra is covered with so many shallow lakes and ponds. Even though it receives very little rain each year, the tundra is technically a cold desert in terms of how little moisture falls from the sky. But the ground holds that moisture like a bowl, and the result is a land dotted with still, dark water from horizon to horizon. Gravity plays its role too. On slopes, the active layer can slowly slide downhill over the frozen ground beneath it. The soil moves like a very slow, very thick river. This process is called solifluction, and it happens because the active layer, when it thaws, becomes heavy and waterlogged and has almost nothing to grip. It creeps downhill, sometimes just a few inches each year, leaving behind curved terraces and rippled hillsides. Over long stretches of time, whole hillsides are reshaped by this quiet, invisible sliding. All of these forces, the expanding ice, the lifting ground, the trapped water, the slow creep of soil down frozen slopes, work together without any plan or purpose. They are simply the laws of physics playing out in a cold place, and yet the result is a world of strange geometry and hidden structure. A land shaped from below as much as from above, patient and precise, built one frozen layer at a time. Permafrost covers about a quarter of all the land on Earth. Think about that for a moment. 1 out of every 4 acres of dry land on this planet has frozen ground somewhere beneath it. That is roughly 9 million square miles of frozen Earth, an area larger than the United States, Canada, and Mexico combined. It stretches across northern Russia, Alaska, Canada, Greenland, and parts of the high mountains far to the south. It is one of the largest single features on the surface of our world, and most people have never heard its name. The depth of permafrost is just as striking as its reach. In some parts of Siberia, the frozen ground goes down more than 4,900 feet. That is nearly a mile of solid, frozen earth beneath your boots. If you could stand at the top of the Empire State Building and look straight down, the permafrost below some parts of Russia would extend almost 4 more buildings deep beneath that. It is not a thin crust. It is a vast, ancient column of cold, and it is genuinely ancient. Some of the permafrost in Siberia and northern Canada has been frozen for more than 700,000 years. That frozen ground was already old when the first modern humans walked the earth. Woolly mammoths roamed above it. Ice ages came and went. Entire civilizations rose and fell on other continents. And all the while, that ground stayed frozen, locked in place, holding its shape through everything. Because permafrost is so old and so deep, it acts almost like a skeleton beneath the tundra. It gives the land its form. Without it, the flat plains of the Arctic would drain and collapse. The shallow lakes would vanish into the soil. The strange geometric patterns pressed into the ground, the polygons and circles and ridges that look almost designed, would slowly smooth away. Permafrost is the reason the tundra looks the way it does. It is the hidden architecture of the whole place. Those geometric patterns are worth pausing on. From the air, the tundra looks like a cracked mosaic. The ground is divided into shapes, mostly 5- and 6-sided polygons that stretch across the land as far as you can see. Each polygon can be anywhere from a few feet across to more than 300 feet wide. The borders between them are slightly raised ridges, and the centers are often lower, sometimes holding small pools of water. These shapes form because water expands when it freezes. In winter, the ground contracts in the cold. Cracks open up. Water seeps in. It freezes and pushes outward. Year after year, the same cracks open and fill and freeze again. Over centuries, the ridges grow. The shapes become more defined. The land organizes itself into this quiet, repeating geometry through nothing more than the physics of freezing water. Some of these ice-filled cracks grow into something much larger. When a crack fills with ice over many years, it can become an ice wedge, a blade of pure ice buried in the ground. Some ice wedges are only a few inches wide. Others grow to be more than 10 feet wide and 30 feet deep. They can take thousands of years to reach full size. If you could slice the earth open, 'em, and look at a cross-section of tundra soil, you would see these wedges fanning out beneath the surface like the roots of a frozen tree. The ground above these wedges sinks slightly as the ice below shifts and settles. That sinking creates the low centers of the polygons. The raised ridges mark where the wedges push the soil upward on either side. The whole surface of the tundra is a map of what lies below. Every dip and rise tells you something about the ice hidden underneath. This shaping of the land by frozen water is not just a local curiosity. It is one of the most powerful forces of erosion and construction in the entire Arctic. Rivers change course because of it. Hillsides tilt, coastlines crumble where permafrost meets the sea and thaws at the edge. In some places along the Arctic coast, the land is eroding at a rate of more than 30 feet per year as the frozen cliffs melt into the ocean. Whole stretches of coastline that existed a generation ago are simply gone. The tundra is not a still or static place, even though it looks that way from a distance. Beneath its quiet surface, ice is always moving, always pressing, always shaping. The land breathes in a language of cold and pressure, written in polygons and wedges and slow, patient geometry. It has been writing that same language for hundreds of thousands of years. Stand on the tundra surface and look down. What you see is not bare dirt. It is something stranger and more alive than that. The soil of the tundra is thin. In most places, it is only a few inches deep before you hit frozen ground. That thin layer is called the active layer, the narrow band of earth that thaws each summer and refreezes each winter. It is the only part of the ground where anything can grow. Everything that lives on the tundra, every root and seed and buried insect, must find a way to exist within that shallow strip of soil. That soil is dark, almost black in places, especially when it is wet. It gets its dark color from dead plant matter that has built up over centuries. In warmer climates, dead leaves and roots break down quickly. Bacteria and fungi consume them fast, returning their nutrients to the soil. But the tundra is too cold for that. Decomposition, the slow process of breaking down dead things, moves at a crawl here. So the organic matter, the old moss and sedge and root material piles up year after year. It compresses, it darkens. It becomes a spongy, dense material called peat. Peat feels soft underfoot. It gives slightly when you step on it, like walking on a very thick, damp sponge. In some parts of the tundra, the peat layer is several feet deep, built up over thousands of years of slow accumulation. It holds enormous amounts of water. After the summer thaw, the peat soaks up snowmelt and rain like a giant sponge, keeping the surface wet and boggy for weeks at a time. That wetness is part of what gives the tundra its particular look in summer. From above, it shimmers. The surface is dotted with shallow pools and dark, wet patches that catch the low Arctic sun. The water does not drain away easily because the permafrost below acts like a sealed floor. Water cannot sink down through frozen ground, so it spreads out sideways, pooling in every low spot. The tundra becomes a mosaic of wet and dry, dark water, and pale sedge grass, all of it glinting under a wide open sky. The colors of the tundra surface shift with the seasons in ways that are hard to forget once you have seen them. In late spring, when the snow first pulls back, the ground is a pale, exhausted brown. The dead stalks of last year's plants lie flat, pressed down by months of snow. The surface looks almost lifeless, but within days, green begins to push through. Thin blades of sedge grass, low mats of moss, tiny flowering plants, no taller than your thumb. The green comes fast, urgent, knowing it has only a short window of warmth. By midsummer, the tundra surface is a patchwork of greens and golds and soft purples. Sedge grasses grow in dense tufts called tussocks. Each tussock is a raised mound of grass, roughly the size and shape of a human head, sitting on a thick base of old dead stems. Walking across a tussock field is slow, awkward work. The mounds are uneven and unstable. You step on one, and it tilts. You step between them, and your foot sinks into cold, wet ground. Animals that live here have learned to move around them. People who travel through the tundra on foot know them well, and not always fondly. The tussocks themselves are a kind of slow architecture. Each one has been growing and dying and rebuilding for decades. The living grass grows from the top. The dead material compresses beneath it, raising the mound a little higher each year. A single large tussock may represent 100 years of patient growth. By autumn, the colors shift again. The sedge grasses turn gold and amber. The low shrubs, the bearberry and crowberry and dwarf birch, flush red and orange. For a few short weeks, the tundra surface burns with color. It is one of the most vivid displays of autumn on Earth. Spread across millions of acres, with no trees to block the view. The sky above is enormous. The light is low and golden. The whole surface glows. Then the snow returns. It covers the tussocks and the peat and the dark pools. It smooths everything into white. The surface goes quiet. The thin, active layer freezes back down. The soil holds its breath again, waiting for the next brief thaw, patient as it has always been, carrying within it the slow record of every season that has passed across this ancient, cold, and quietly extraordinary land. Beneath that white blanket, something remarkable is waiting. The tundra is not just a surface. It is a world with layers, each one holding its own quiet secrets. And the deeper you look, the more extraordinary it becomes. Start just below the snow. The active layer, that thin band of soil that thaws each summer, is where most of the tundra's plant life takes root. But these roots do not go deep. They cannot. The frozen ground below stops them cold. So tundra plants spread sideways instead of downward. Their root systems fan out wide and flat, just beneath the surface, like a web of fine threads pressed between two panes of glass. This shallow root network is one of the great adaptations of tundra life. It lets plants drink from the thin layer of meltwater that pools above the permafrost each summer, even when the soil below is still locked in ice. Some tundra flowers are so small they seem almost impossible. The purple saxifrage grows in tight, cushion-shaped mounds, hugging the ground to stay warm. It is one of the first flowers to bloom each spring, sometimes pushing up through the last of the snow, while the air above is still bitterly cold. Its tiny purple petals are vivid against the pale ground. Scientists have found purple saxifrage growing at some of the highest latitudes on Earth, closer to the North Pole than almost any other flowering plant. It survives because its cushion shape traps heat from the sun, creating a small warm zone just inside the plant itself. The temperature inside a saxifrage cushion can be several degrees warmer than the air just inches away. That ability to hold heat is shared by many tundra plants. The Arctic poppy, with its pale yellow or white petals, grows on a flexible stem that slowly rotates to follow the sun across the sky. This movement is not accidental. The poppy's bowl-shaped flower acts like a small dish, focusing sunlight toward its center. Insects that land inside the flower find a pocket of warmth, and they stay longer, carrying more pollen when they leave. The plant feeds the insect. The insect serves the plant. Even here, in one of the coldest places on Earth, life finds ways to cooperate. Below the roots, the soil itself tells a long story. Tundra soil is dark and rich in organic matter. The broken down remains of plants that have been dying and accumulating for thousands of years. This layer is called peat, and it builds slowly. In some parts of the tundra, the peat layer is several meters thick, representing tens of thousands of years of plant material that never fully decomposed because the cold slowed the process almost to a stop. Scientists can drill down through this peat and read it like a record. Pollen grains from ancient plants are preserved inside it. Tiny seeds, insect parts, even fragments of ancient moss remain intact. Each layer is a snapshot of what was growing here long ago, when the climate was slightly different, when the tundra itself was younger. Deeper still, the permafrost holds even older things. Mammoths have been found frozen inside it, their fur and skin, and even their last meals still preserved after tens of thousands of years. These are not fossils in the usual sense. They are not bones turned to stone. They are the actual animals frozen whole, locked inside the earth as if time simply stopped for them. Scientists have recovered ancient seeds from permafrost deposits and successfully grown plants from them. Plants whose ancestors lived during the last ice age. The frozen ground is a vault, and it has been keeping its contents safe for longer than human civilization has existed. Even the bacteria living in permafrost are extraordinary. Scientists have found living microbes in permafrost layers that are hundreds of thousands of years old. These tiny organisms have been dormant, neither fully alive nor fully dead, waiting in the cold for conditions to change. When researchers bring them into warmer temperatures, some of them wake up. They begin to move and feed again, as if no time has passed at all. The tundra's depths are full of life that exists on a timescale almost impossible to imagine. All of this, the shallow roots, the heat-gathering flowers, the ancient peat, the frozen vault below, forms a single connected system. The surface and the depths are not separate. They breathe together. What happens at the top shapes what is preserved below. What is locked in the deep shapes what can grow above. The tundra is not just a cold and empty place. It is a living archive, patient and deep, holding within it the long memory of this planet's past. And yet, for all the stillness locked beneath the surface, the tundra above is not motionless. It moves. It breathes in cycles. It changes with the seasons in ways that are slow and quiet and deeply strange. Consider the trees. Most of us picture trees as tall things, straight trunks reaching upward, branches spread wide against the sky. But in the tundra, trees have learned a different way. They grow low. They grow sideways. They press themselves close to the ground, as if the earth itself is offering shelter from the wind. The most remarkable of these is the dwarf willow. It is a true tree with roots and bark and seeds, but it rarely grows taller than a few inches. In some parts of the Arctic, a dwarf willow that is only as tall as your thumb may be over 100 years old. It has spent a century growing sideways, hugging the ground, staying just below the level where the wind tears hardest across the open plain. This is not weakness. This is patience. This is a tree that has found its own way to survive. The reason trees grow this way comes down to one of the tundra's most powerful forces: the wind. Cold air in the Arctic moves fast and carries ice crystals with it. Any branch that rises above the snowpack gets sandblasted through the long winter. The snow itself, strange as it sounds, acts like a blanket. plants and branches buried under it stay warmer than the air above. So trees that stay low, that keep themselves tucked beneath the snow, survive. The ones that reach too high do not. This creates a kind of invisible ceiling in the tundra. Scientists call it the Krumholtz zone, from a German word meaning crooked wood. It is the boundary where upright trees give way to creeping, twisted, ground-hugging forms. Walk through this zone, and you feel like you have entered a different world. The trees look ancient and gnarled, bent by decades of wind into shapes that seem almost deliberate, like something sculpted by hand. The growth cycle of these trees follows the tundra's own rhythm. In winter, they are buried and still. In the brief Arctic summer, they burst into action. Dwarf willows push out leaves and catkins, the small, soft flower clusters that carry their pollen in a matter of days. They have to. The growing season in the high Arctic can be as short as 6 to 8 weeks. Every day of warmth counts. Every hour of sunlight is used. This short and urgent growing season shapes everything about how tundra plants cycle through their lives. They do not grow slowly and steadily the way a tree in a temperate forest might. They sprint. They pour all their energy into leaves and seeds as fast as they can, then pull back as the cold returns. Some plants complete their entire reproductive cycle, from bud to seed, in under 3 weeks. It is one of the fastest life cycles of any woody plant on Earth. And then there is the cycle of the land itself. The tundra surface does not stay still from year to year. Freeze and thaw, repeated over centuries, pushes the ground into patterns. Stones get sorted by size and pushed into rings and stripes across the hillsides. This process is called frost heaving, and it works like this. When water in the soil freezes, it expands. That expansion pushes rocks upward and outward. Over many winters, larger rocks migrate to the edges of these expanding ice lenses, and smaller material stays in the center. The result is a landscape covered in geometric shapes, circles and polygons, and long parallel lines, as if someone has drawn careful patterns across the ground. These shapes form over hundreds of years and shift slowly with each passing season. The tundra, then, is not a frozen and static place. It pulses. The soil heaves and settles. The plants sprint through summer and retreat into stillness. The trees crawl across the ground, growing inch by inch, decade by decade, following a rhythm measured not in years, but in centuries. Every cycle connects to the others. The freeze and thaw that sorts the stones also cracks the soil, creating pockets where seeds can settle. The low-growing willows trap snow, which insulates the ground below, which slows the freeze, which changes how deep the permafrost sits. Nothing works alone. Each rhythm feeds into the next, the way a slow river shapes the valley it flows through, one quiet season at a time. The tundra moves. It just moves on a timescale that asks you to slow down and look carefully before you can see it. Among all the living things that call the tundra home, two stand apart. They are not flowers. They are not trees. They are not even what most people picture when they think of plants. Lichen and moss are the quiet pioneers of the frozen world. They were here long before the willows and the sedges. They will likely be here long after. And they do more to hold this cold place together than almost anything else alive. Lichen is not one thing. It is two. A lichen is a partnership between a fungus and an alga. Two completely different organisms living so closely together that they function as a single creature. The fungus builds the structure, a tiny branching or leafy body that can grip bare rock or frozen soil. The alga lives inside that structure and uses sunlight to make food, which it shares with the fungus. Neither one could survive alone in the tundra's harsh conditions. Together, they thrive. Scientists call this kind of relationship symbiosis, where two organisms live in close contact and both benefit. In the tundra, symbiosis is not a rare exception. It is a survival strategy. Lichen can grow on bare rock where nothing else can get a foothold. It releases weak acids that slowly break the rock surface down, pulling out minerals and creating the first thin layer of something that will, over thousands of years, become soil. This process is called weathering. It is extraordinarily slow. A lichen crust, a few centimeters thick, may represent centuries of patient work. But that thin crust is the beginning of everything. Without it, the Tundra's soil would be even poorer than it already is. Lichen does not just live on the land, it helps build it. Some tundra lichens grow in thick, spongy mats across the ground, pale gray-green and almost luminous in flat Arctic light. One of the most important is called reindeer lichen, or caribou moss, though it is not a moss at all. It forms dense, branching cushions that carpet wide stretches of open tundra. Caribou depend on it heavily, especially in winter, when they use their hooves to scrape through snow to reach it. A single caribou can eat several pounds of lichen in a day. The lichen grows back, but slowly, sometimes taking decades to fully recover after heavy grazing. The relationship between caribou and lichen is one of the oldest and most finely balanced in the Arctic world. Moss works differently, but it is just as essential. Mosses are true plants, small and rootless, drawing water directly through their leaves. They grow in dense, soft mats in the wetter parts of the tundra, along stream banks, around ponds, in low spots where snowmelt collects. Some mosses can absorb many times their own weight in water, acting like a living sponge across the landscape. This matters enormously. The tundra's soil drains poorly because permafrost sits just below the surface and blocks water from sinking down. Moss soaks up that standing water, holds it, and releases it slowly. It regulates moisture the way a sponge regulates a puddle. Moss also insulates the ground. A thick mat of living moss can keep the soil beneath it several degrees cooler than the air above. This slows the thaw of the permafrost below. Scientists studying tundra ecosystems have found that where moss cover is thick, permafrost stays more stable. Where moss is removed or disturbed, the ground warms faster and the permafrost retreats. The moss is not just living on the tundra, it is actively protecting it. Both lichen and moss can survive conditions that would kill most other living things. They can dry out completely, entering a kind of suspended state, and then rehydrate and resume growing when moisture returns. Some species have been revived after being frozen for years. They have no roots to freeze, no soft tissue to burst. They simply wait. This patience is their great gift. In a place where survival depends on enduring long stretches of cold and dark. Lichen and moss have perfected the art of waiting. They are also among the first organisms to colonize land after a glacier retreats. When ice pulls back and leaves bare rock behind, lichen arrives first, gripping the stone, beginning the slow work of breaking it down. Moss follows, filling the cracks, holding moisture, building the thin skin of soil that other plants will eventually need. This sequence, lichen first, then moss, then grasses and sedges, and eventually shrubs, is called ecological succession. The tundra we see today is the result of that succession playing out across thousands of years, one patient organism at a time. Everything in this cold world leans on something else. The lichen feeds the caribou. The moss protects the permafrost. The permafrost shapes the soil. The soil supports the flowers. The chain is long and quiet and remarkably strong. And the caribou that feed on that lichen do something remarkable. They move, not just a little, not just from one hillside to the next. Some caribou herds travel up to 3,000 miles in a single year. That is the longest overland migration of any land animal on Earth. They walk from their winter grounds in the boreal forest, the great belt of spruce and pine just south of the tundra, all the way north to the open Arctic plains, where they will give birth and feed through the brief summer. Then they turn around and walk back. Every year, without fail. The herds that make this journey are enormous. The western Arctic caribou herd in Alaska once numbered close to 500,000 animals. When they move together across the open tundra, the sound carries for miles. The low rumble of hooves on frozen ground, the soft clicking of their ankle joints, a sound unique to caribou, fills the air like a slow, steady drumbeat. That clicking comes from a small tendon that snaps over a bone with each step. Scientists believe it helps the animals keep track of each other in blinding snow and fog, when they cannot see, but can still hear the herd moving around them. Caribou hooves are built for this life in a way that feels almost designed. In summer, the hooves soften and spread wide, giving the animal grip on wet, spongy tundra. In winter, the same hooves harden and sharpen, acting like ice picks on frozen ground and snow. The hooves also work like shovels. Caribou dig through snow to reach the lichen underneath, a behavior called cratering. They can smell lichen buried under 2 feet of snow. They will dig through ice crust, through wind-packed drifts, through layers that would exhaust most animals, just to reach that pale, papery food below. The routes these herds travel are not random. They follow the same paths year after year, generation after generation. The land itself shows this. In some parts of the Arctic, you can see the caribou trails worn into the earth. Long parallel lines etched across hillsides and valley floors, visible from the air. These are not modern roads. Some of these trails are thousands of years old. The animals that walk them today are following paths their ancestors wore into the ground long before any human mapped this land. And the tundra holds other extreme travelers. The musk ox is not a traveler in the same way. It stays. While caribou flee the worst of winter by heading south, the musk ox stands its ground. These animals endure some of the coldest temperatures any large land mammal faces. They have survived on the tundra for hundreds of thousands of years, through ice ages that buried much of the northern world. Their coat is the key. The outer layer is made of long, coarse guard hairs that hang nearly to the ground. Beneath that is a layer of soft, fine wool called kiviut, one of the warmest natural fibers known. Kiviut is said to be 8 times warmer than sheep's wool. A musk ox standing still in a -40-degree wind is losing very little heat at all. When wolves approach, musk oxen do not run. They form a circle, adults facing outward, calves protected in the center. This defense has worked for a very long time. It held off wolves and lions and short-faced bears during the last ice age. It still works today. The circle is one of the oldest survival strategies on Earth, and the tundra is where it has been practiced the longest. The tundra also holds records underground. The oldest known permafrost, the permanently frozen ground beneath the surface, is found in Siberia and is estimated to be around 700,000 years old. Inside that ancient frozen ground, scientists have found the preserved remains of woolly mammoths, ancient horses, and bison. their fur and skin still intact, their last meals still visible in their stomachs. The cold stopped time for them. They are windows into a world that no longer exists, kept perfectly still by the same frozen ground that shapes every hillside and pond and polygon on the tundra surface today. The extremes here are not just records on a chart. They are living proof of what endurance looks like. The caribou walking 3,000 miles. The musk ox standing still in the killing cold. The permafrost holding its memories for 700,000 years. Each one pushes against the limits of what seems possible. Each one has found its own way to survive in a place that offers very little mercy and asks everything in return. Among all the animals that call the tundra home, few carry its story as quietly as the Arctic fox. This small creature weighs only about 7 to 17 pounds. It is not much bigger than a house cat, and yet it survives winters that would kill almost anything else in one of the coldest places on the surface of the earth. The secret begins with its coat. In winter, the Arctic fox wears thick white fur. The white is not just beautiful, it is a disguise. Against the snow-covered tundra, the fox becomes almost invisible. A pale shape moving across a pale world. Predators look past it. Prey does not see it coming. The coat does two jobs at once, and it does both of them perfectly. Then something remarkable happens. As spring arrives and the snow begins to pull back from the land, the fox's coat changes color. It shifts from white to a brownish gray, sometimes with hints of blue. This new coat matches the exposed rocks and muddy ground of the summer tundra. Scientists call this seasonal camouflage, meaning the animal's color changes with the seasons to help it blend in. No other land animal on Earth does this quite so completely or so reliably. The fur itself is extraordinary in ways that go beyond color. The Arctic fox has the warmest fur of any mammal studied in relation to its body size. Its coat contains two layers. The outer layer is made of long, coarse guard hairs that shed wind and moisture. Beneath that sits a dense, soft underlayer called underfur, which traps warm air close to the skin like a natural insulating blanket. Together, these two layers allow the fox to stay comfortable in temperatures as low as -70 degrees Fahrenheit. It does not begin to shiver until the cold drops below that point. Most mammals would be in serious danger long before reaching that threshold. Its paws are also covered in fur, including the bottoms. This is rare among mammals. Those furry soles act like small snowshoes, spreading the fox's weight across the snow and keeping its feet from losing heat through direct contact with frozen ground. Every part of this animal has been shaped over thousands of generations to fit the tundra like a key fits a lock. The Arctic fox is also a remarkable traveler. Scientists have tracked individual foxes crossing enormous distances in search of food. One fox, tracked by researchers in Norway, traveled more than 2,700 miles in just 76 days, crossing sea ice from Svalbard all the way to Canada. It moved at an average of about 28 miles per day. That journey, made by a small animal roughly the size of a rabbit, crossed one of the most remote and hostile stretches of terrain on the planet. Food is always the central challenge. In winter, the fox follows polar bears across the sea ice, eating the scraps left behind from a bear's seal kill. It is a patient strategy. The fox waits at a careful distance, watching, and then moves in when the larger animal has finished. In summer, the fox shifts its diet entirely. It eats lemmings, birds, eggs, berries, and even seaweed along the coast. This flexibility is part of what makes it so successful. The tundra rarely offers the same meal twice, and the Arctic fox has learned to eat almost anything. During the brief summer abundance, the fox does something that seems almost impossible for such a small animal. A single litter can contain up to 14 pups, one of the largest litter sizes of any wild canid. The family of animals that includes wolves, dogs, and foxes. The parents work constantly through the long summer days, hunting and carrying food back to the den. The pups grow quickly. They have to. By the time the cold returns, they must be ready to survive on their own. The den itself is often dug into a hillside or riverbank, sometimes in the same location that foxes have used for hundreds of years. Scientists have found tundra dens that show signs of continuous use going back more than a century. The same sheltered slope, the same tunnels worn smooth, passed from one generation to the next without ceremony or memory, just instinct and the reliable warmth of a south-facing hillside. There is something deeply calming about the Arctic fox. It does not fight the tundra. It does not resist the cold. It simply fits into it, changing its coat, following the bears, feeding its pups in the long light of summer, and waiting out the dark in a den that has held foxes longer than anyone alive can remember. It belongs here, completely, quietly, and without question. Not far from where the Arctic fox makes its den, something much larger moves across the ice. The polar bear is the biggest land predator on Earth. A full-grown male can weigh more than 1,500 pounds and stand nearly 10 feet tall on his hind legs. He moves with a slow, rolling walk that looks almost lazy. But that walk covers ground quickly, and the bear misses very little. Polar bears live at the edge of the tundra, where the frozen land meets the frozen sea. They are creatures of two worlds. They sleep and give birth on land, but they hunt almost entirely on the sea ice. That vast white platform of frozen ocean that forms each winter and breaks apart each spring. The sea ice is not just a place they visit. It is the center of their lives. Their main prey is the ringed seal. Seals must breathe air, so they carve small holes up through the ice and return to those holes again and again. The polar bear finds these holes by smell. Scientists believe a polar bear can detect a seal through 3 feet of solid ice and snow. The bear waits beside the hole in total stillness, sometimes for hours, until the seal surfaces. Then it strikes with one powerful blow. The whole hunt depends on patience and ice. Without the ice, there is no hunt. For most of human history, the polar bear was a creature of rumor. Sailors and traders who traveled the northern seas brought back stories of enormous white bears that swam in open water and showed no fear of men. These stories were hard to believe. A bear that lived on ice, that swam between floes, that hunted seals in the dark of winter. It sounded like invention, but the stories were true. The first careful written records of polar bears in European science came from the voyages of the 1500s and 1600s, when Dutch and English explorers pushed north, looking for trade routes through the Arctic. Willem Barents, a Dutch navigator, led expeditions into the high Arctic in the 1590s. His crew encountered polar bears on the island of Novaya Zemlya, off the northern coast of Russia. The bears were aggressive and enormous. One encounter ended with sailors fighting off a bear that had dragged a crewman away. Barents and his men were among the first Europeans to record detailed observations of polar bears in the wild. And they did so not in a laboratory, but in a desperate struggle to survive the winter ice. What those early explorers could not have known was how perfectly the polar bear is built for this world. Its fur looks white, but each individual hair is actually a hollow, clear tube. The hollow structure helps trap warmth close to the bear's black skin, which absorbs heat from sunlight. The paws are enormous, acting like snowshoes on soft snow and paddles in open water. The fat layer beneath the skin can be 4 inches thick. Every part of the animal is shaped by millions of years of living in the cold. Female polar bears give birth in dens dug into snowdrifts on land. They enter the den in late autumn, already pregnant, and they do not eat or drink again until spring. Inside the den, in total darkness and deep cold, they give birth to cubs that weigh less than 2 pounds each. By the time the mother leads them out onto the ice in March or April, the cubs have grown large enough to travel. The mother has lost nearly half her body weight feeding them through the winter without eating anything herself. It is one of the most extreme acts of care in the animal world. Scientists began studying polar bears in a serious and systematic way in the 20th century. Early researchers had to travel by dog sled and small boat to reach the bears at all. Later, researchers used tranquilizer darts fired from helicopters to safely capture bears, weigh them, take blood samples, and attach radio collars that could be tracked by satellite. These studies revealed something that earlier explorers could not have guessed. Polar bear populations are not spread evenly across the Arctic. They live in distinct groups, each tied to a particular stretch of sea ice, each following the same seasonal rhythms year after year. The sea ice those bears depend on is changing. It forms later in the year now, and it breaks up earlier. The bears have less time to hunt. Some populations have grown thinner over the decades. The animal that Dutch sailors once described as impossibly powerful, a creature of myth made real, now faces a world that is shifting beneath its enormous paws. The ice that built it is slowly pulling away. While the polar bear waits on shrinking ice, something else is happening above the tundra. Look up. The sky is full of wings. Every spring, birds arrive at the tundra in numbers that are almost hard to believe. They come from every direction. They come from every corner of the planet. Some have flown thousands of miles just to reach this cold and open ground. The tundra, which looks so empty and so still for most of the year, becomes one of the most crowded places on Earth for a few short months. The Arctic tern makes the longest migration of any animal alive. This small, silver-white bird with a red beak weighs less than 4 ounces. It is lighter than a handful of grapes. And yet, it travels from the Arctic to the Antarctic and back again every single year. That round trip covers roughly 50,000 miles over the course of its lifetime, which can last 30 years or more. A single Arctic tern may travel the equivalent of 3 trips to the moon and back. Scientists confirmed this only recently, using tiny tracking devices light enough not to burden the birds in flight. The data came back, and even the researchers were surprised. The tern does not make this trip for the scenery. It follows the light. The Arctic summer brings nearly endless daylight, and so does the Antarctic summer on the other side of the year. By chasing the sun across the globe, the Arctic tern lives in more daylight than any other creature on Earth. It is always moving toward warmth and food, always riding the long, bright hours. Other birds come to the tundra for different reasons. The tundra offers something rare and valuable in the animal world. Open, flat ground with almost no trees to hide predators, and an explosion of insects in summer that provides more food than almost anywhere else on the planet. For birds that nest on the ground, this is ideal. Shorebirds fly in from South America. Geese arrive from the Gulf Coast of North America. Wading birds come from the coasts of Africa and Europe. The tundra pulls them all in like a magnet. The red knot is one of the most remarkable of these travelers. This small, rust-colored shorebird breeds on the high Arctic tundra and then flies south to the very tip of South America. A journey of nearly 10,000 miles each way. Along the route, it stops at specific beaches to feed, building up fat reserves before the next long leg of flight. Scientists have found that red knots can nearly double their body weight before a major migration push, burning through that stored fat like fuel in an engine. Their internal organs actually shrink during the flight to reduce weight, then grow back once they land. The body reshapes itself for the task. What draws all of these birds to the tundra specifically is the timing. The Arctic summer is short, but it is intense. The permafrost below the surface keeps meltwater from draining away. So the ground becomes dotted with shallow ponds and wet meadows. Those wet areas breed insects by the billions. Mosquitoes, midges, and flies hatch in enormous clouds. For a bird raising chicks, this is a feast. The food is everywhere, easy to catch, and almost endless for a few precious weeks. The birds arrive, breed quickly, raise their young on the insect bloom, and then leave before the cold returns. The snow goose uses this window with extraordinary efficiency. Flocks of snow geese descend on the tundra in spring, and the females begin nesting almost immediately. The timing is so precise that researchers have found snow geese can adjust their arrival date based on how early the snow melts in a given year. They track environmental signals across thousands of miles of travel and fine-tune their schedule accordingly. The tundra's brief summer and the birds' internal clocks are locked together in a rhythm that has been running for thousands of years. There is something quietly astonishing about all of this. A bird the size of your fist, born on a frozen plain at the top of the world, carries a map inside its body. It knows where to go. It knows when to leave. It finds finds the same beaches, the same feeding grounds, the same nesting sites year after year. The tundra calls to it across half the globe, and the bird answers. The sky above the tundra is never truly empty. Even in the coldest months, the snowy owl moves silently over the snow. Even in the darkest weeks, the raven calls from somewhere out in the white. The birds never fully leave this place. They are woven into it, season after season, in ways that took scientists decades to begin to understand. But the sky is only part of the story. Beneath the snow, a whole other world is quietly alive. When winter settles over the tundra, the surface becomes a blank white sheet. Nothing moves. Nothing seems to breathe. But just below that frozen crust, in the thin space between the ground and the snow above, small creatures are going about their lives. This hidden layer has a name. Scientists call it the subnivean zone, the world under the snow, and it is warmer than you might expect. Snow is a surprisingly good insulator. The tiny air pockets trapped between snowflakes hold heat close to the ground. Even when temperatures above the snow drop to 30 or 40 degrees below zero, the subnivean zone can stay near the freezing point. That difference is enormous. It is the difference between survival and death for dozens of small animals. The meadow vole is one of the tundra's most remarkable winter survivors. This small, round creature, about the size of a child's fist, does not hibernate. It does not migrate. It simply moves downward. Beneath the snow, voles build tunnels and nesting chambers lined with dry grass. They move through these tunnels all winter long, eating seeds and dried plant material they stored in autumn. Their heart rates slow slightly in the cold, but they stay active. They stay warm. They are busy beneath the snow while the world above them stands perfectly still. The lemming does the same. Lemmings are famous for their population booms, years when their numbers explode across the tundra in great waves. But even in quiet years, lemmings spend the winter tunneling through the subnivean zone, feeding, breeding, and raising young. A female lemming can give birth to a litter of pups beneath the snow in the middle of winter. By the time spring arrives and the snow melts away, there may be many more lemmings than there were in autumn. This surge of small bodies feeds everything above. The snowy owl that hunts through the dark months, the Arctic fox that pads silently across the frozen plain. Both of them depend on what is happening beneath the snow. The subnivean zone does not just shelter small animals, it feeds the larger ones. This is how the tundra works. Each layer connects to the next. The snow insulates the ground. The ground shelters the voles. The voles feed the foxes. The foxes keep the vole population from growing too large. And when the foxes have a good year, they raise more pups, which grow up and spread across the tundra, keeping the balance steady. Pull one piece away, and the whole system shifts. Even the plants are part of this. Beneath the snow, the roots of tundra grasses and sedges stay alive all winter. They are not growing exactly, but they are not dead either. They are waiting, and the voles and lemmings that tunnel through the subnivean zone feed on the dried stems and seeds of these same plants. The plants feed the small animals. The small animals, when they die, return nutrients to the soil. The soil feeds the plants again. It is a slow, patient loop that has been running for thousands of years. The weasel, specifically the short-tailed weasel, also called the ermine, takes this connection one step further. The ermine is small enough to follow lemmings directly into their tunnels. It turns white in winter, matching the snow above. It hunts beneath the surface, moving through the same passages the lemmings built. The ermine is so perfectly shaped for this that its body is almost tubular, long and narrow, built to slide through tight spaces. It is a predator designed by the tundra itself, shaped by millions of years of hunting in the dark beneath the snow. And when spring finally comes and the snow melts away, all of this hidden life rises to the surface. The voles emerge, blinking into the light. The lemmings scatter across the open ground. The ermine's white coat begins to shift back toward brown. The owls and foxes follow the animals upward, hunting in the open air once more. The subnivean world dissolves, and the tundra's summer begins. What is astonishing is how complete this hidden world is. It has its own food chains, its own shelters, its own rhythms of birth and death. It exists in a space just a few inches thick, sandwiched between between frozen earth and frozen sky, and yet it sustains life through the longest, darkest months the tundra has to offer. The snow does not just cover the tundra. In a very real way, the snow keeps it alive. When spring arrives and the snow finally pulls back, something unexpected begins to happen. The tundra, which most people picture as a silent and frozen place, starts to hum. Not loudly, not all at once, but steadily and with growing force, the insects come. This surprises many people. The tundra is not a place you associate with buzzing wings or crawling legs. It is too cold, too harsh, too bare. And yet insects have lived here for a very long time. Mosquitoes, midges, blackflies, and bumblebees all call the tundra home for at least part of the year. In summer, they emerge in numbers that can be genuinely staggering. Swarms of mosquitoes rise from the thawing wetlands so thick that they can darken the air above the ground. Scientists have recorded more than 30 species of mosquito living above the Arctic Circle. The mosquitoes are not just a nuisance. They are a critical piece of how the tundra feeds itself. Billions of them hatch from the shallow ponds and waterlogged soil each summer. They become food for birds, for fish, for bats, and for other insects. Without them, the entire chain of summer feeding would weaken. The caribou, which we have already met on their long roads across the tundra, are tormented by these swarms. A single caribou can lose more than a liter of blood in a single week to biting insects. The animals move constantly, seeking higher ground and stronger winds to escape. The insects shape the behavior of animals far larger than themselves. Bumblebees are perhaps the most remarkable insect story the tundra has to tell. They are warm-blooded in a way that most insects are not. A bumblebee can shiver its flight muscles to generate heat, raising its body temperature well above the cold air around it. This lets it fly and forage in temperatures that would ground most other insects entirely. On the tundra, where summer is short and flowers bloom quickly, this ability matters enormously. The bumblebee can work earlier in the morning and later into the evening than any other pollinator. It is one of the only insects that can function in near-freezing air. But here is where the story of tundra insects begins to shift. The tundra is changing, and the insects are changing with it. The Arctic is warming roughly 4 times faster than the rest of the planet. Summers are growing longer. The snow melts earlier in the spring and returns later in the fall. For insects, this is an invitation. Species that once lived far to the south are now moving north, following the warmth into territory that was previously too cold for them to survive. Scientists have begun documenting insects in parts of the Arctic where they were never recorded before. Some of these newcomers are harmless. Others are not. Bark beetles, which tunnel into trees and kill them, have expanded their range northward as winters grow milder. In the boreal forest just south of the tundra, they have already caused widespread tree death across millions of acres. As the tree line itself creeps north, the beetles may follow. There is also the question of timing. Many tundra plants and insects have evolved together over thousands of years. A flower blooms at a certain moment. An insect emerges at a certain moment. The two events line up and pollination happens. But warming is shifting these schedules, and not always at the same rate. A plant might bloom earlier because of warmer soil. The insect it depends on might not emerge earlier because it responds to a different signal, perhaps the length of the day rather than the temperature. When the two fall out of step, pollination fails. Seeds are not made. The plant struggles to reproduce. This kind of mismatch, where two things that once worked together begin to drift apart, is one of the quieter and more troubling changes happening across the tundra right now. It does not make headlines. It does not look dramatic from above. But in the small, intricate relationships between flowers and the creatures that visit them, something is slowly coming loose. And yet the insects themselves are not to blame. They are simply doing what living things do. They are following warmth. They are filling space that opens up before them. They are responding to a world that is moving faster than it has in a very long time. The tundra has always changed. Ice ages have come and gone. Species have arrived and departed over thousands of years. But the speed of what is happening now is something different. The tundra is being asked to adapt not over millennia, but over over decades. And the insects, small as they are among the first signs that the answer to that question is already being written. And then, after all that long waiting, the light comes back. It does not arrive gently. It does not ease in the way light does in softer places. In the Arctic tundra, summer arrives like a door swung wide open. One day the sun barely clears the horizon. Then, weeks later, it simply does not set at all. This is the midnight sun. For weeks at a stretch, the sun circles the sky without ever dipping below the edge of the world. At 2 a.m, the light is golden and low and warm-looking, slanting across the flat land in long amber ribbons. The sky never goes dark. The stars disappear entirely. The tundra, which spent months under a pale and distant light, is suddenly bathed in something close to endless day. This happens because of the tilt of the Earth. Our planet leans at an angle as it travels around the sun. In summer, the northern polar regions tilt toward the sun so steeply that the sun never fully sets. Above the Arctic Circle, that line sitting at about 66 degrees north latitude, the midnight sun can last for weeks or even months, depending on how far north you stand. At the very top of the world, the North Pole itself, the sun stays above the horizon for roughly 6 months straight. That light is not wasted. The tundra drinks it in. Plants that spent the winter frozen solid begin to stir. The ground thaws at the surface, just a thin layer above the permafrost below. And into that thin, wet, newly warmed soil, the tundra erupts. The word erupts is not too strong. Within days of the thaw, grasses green up, sedges push through standing water, and flowers open in colors that seem almost impossible for such a harsh place. There are bright yellows, deep purples, soft pinks, and clean whites scattered across the ground like something spilled from a painter's hand. The Arctic poppy is one of the most striking of these. It is a small flower, delicate looking, with thin petals the color of pale sunshine. But it has a remarkable trick. The flower turns to face the sun and tracks it across the sky throughout the day, the way a satellite dish rotates to stay locked on a signal. Scientists call this behavior solar tracking, or heliotropism. The cup shape of the flower focuses the sun's warmth toward its center, raising the temperature inside the bloom by several degrees compared to the air around it. This warmth attracts insects looking for a warm place to land. The flower uses light not just to grow, but as a tool. The tundra in summer is not a quiet place. It buzzes and hums. Millions of insects fill the air. Shorebirds that flew thousands of miles to reach this place work the wet ground in a constant, focused search for food. The sky above is busy with wings. The land below is alive with movement. All of it powered by that long, low, golden light. And the light itself has a quality unlike anywhere else on Earth. Because the sun stays low on the horizon, even at its highest point, it never beats straight down the way it does in the tropics. Instead, it comes in at a long angle, stretching every shadow out across the ground. Rocks cast shadows 10 times their own length. A single flower throws a thin, dark line across the moss. The whole tundra glows from the side rather than from above, and everything in it looks lit from within. Photographers travel from all over the world to stand in this light. It is called the golden hour in most places, that brief window just after sunrise or before sunset, when the light turns warm and soft. In the Arctic summer, the golden hour lasts all night. The bloom itself is brief. The tundra's growing season is one of the shortest of any ecosystem on Earth. In many places, plants have fewer than 60 days to grow, flower, set seed, and prepare for the next winter. Some years, the season is even shorter. Every warm day matters. Every hour of light is used. There is something quietly moving about watching the tundra in summer. This land, which endures so much cold and darkness for so long, does not hold back when the light finally arrives. It gives everything it has. The flowers open fully. The animals move with purpose. The whole place leans into the warmth with a kind of total commitment that is hard to describe and easy to feel. The light does not last. But while it is here, the tundra is one of the most alive places on the surface of this planet. And then the water comes. When the tundra's brief summer arrives, the snow and the top layer of frozen ground begin to melt. But the permafrost below, that deep layer of permanently frozen earth, does not thaw. It stays hard and sealed like a floor of stone. The meltwater has nowhere to go. It cannot sink down. It cannot drain away. So it spreads across the surface of the land, pooling in every low spot, filling every hollow, turning the tundra into one of the most waterlogged places on Earth. The result is something you have to see to believe. Thousands of lakes and ponds appear, scattered across the plain like pieces of a broken mirror. From the air, the tundra in summer looks more like water than land. In some parts of Alaska and Siberia, lakes and ponds cover more than half the surface. The ground between them is soft and spongy, soaked through, trembling slightly when you walk on it. This is not swamp in the way most people picture it. It is something quieter, something more still. And the sounds of this place are unlike anywhere else on Earth. Stand at the edge of one of these shallow ponds in July and close your eyes. The first thing you hear is wind. The tundra is almost always windy. There are few trees to slow it down, and the flat open land gives it a long, clear run. The wind moves across the water and makes a soft, low hiss. It bends the sedge grasses, those tall, thin plants that grow in dense clusters at the water's edge, and they make a dry, papery, rustling sound, like someone slowly turning the pages of an old book. Then the birds begin. The tundra's lakes and ponds are some of the most important bird nesting grounds on the planet. Millions of shorebirds, ducks, geese, and loons arrive each summer to raise their young in this waterlogged world. The calls of red-throated loons carry across the water with a sound that is hard to describe. It is mournful and wild at the same time, a long, wavering cry that seems to belong to a much older world. Loons are ancient birds. Their lineage stretches back tens of millions of years. When you hear one call across a still Arctic pond, you are hearing something that has echoed across this planet for a very long time. Beneath the surface of the water, there is sound too. In summer, tundra ponds fill with the larvae of midges and other small insects. They move through the water in enormous numbers, and the collective motion of millions of tiny bodies creates a faint, almost imperceptible imperceptible vibration. Fish, where they exist, add their own quiet presence. Arctic grayling, a silver fish with a tall, sail-like fin on its back, move through the deeper lakes with slow, steady sweeps of their tails. And then there is the ice. Even in summer, thin sheets of ice can form on the ponds overnight when temperatures drop. In the morning, as the air warms, that ice cracks. The sound is sharp and clean, like a single note struck on glass. It rings out across the still water and then fades. Sometimes, a larger sheet breaks apart with a deeper, groaning sound, a low creak that travels across the surface before disappearing into the open air. These are small sounds, gentle sounds, but in a place as quiet as the tundra, they carry far. The ponds themselves are not permanent. Over decades, a tundra lake can slowly drain as erosion cuts a channel through its bank. Or it can grow, eating into the surrounding land as permafrost thaws along its edges. Some lakes vanish entirely within a human lifetime. Others have been sitting in the same hollow for thousands of years, their surfaces reflecting the same pale sky, their shores visited by generation after generation of the same species of bird. There is a rhythm to all of it. The freeze and the thaw, the arrival of the birds and their departure, the cracking of the ice in the morning and its slow return at night. The tundra is not a silent place, even though it can feel that way at first. It is a place of small, precise sounds. Sounds that ask you to slow down and listen carefully before you can hear them. The water that fills these ponds fell as snow months ago. It traveled through the cold air, settled on the frozen ground, and waited. Now it sits in the open light, alive with birds and insects, and the quiet creak of melting ice. Nothing here is wasted. Everything moves in its time. The tundra covers roughly 10% of Earth's land surface. That is a vast amount of ground. Spread across the top of the world, it stretches over about 11.5 million square miles. To picture that, imagine the entire continent of North America. Now imagine it nearly 4 times over. That is the tundra's footprint on this planet. Numbers like that carry weight. But the tundra's role in Earth's climate is not just about size. It is about what that cold, open land actually does. And what it does is remarkable. The tundra is one of the planet's great reflectors. Snow and ice bounce sunlight back into space rather than absorbing it. Scientists call this albedo, which simply means the measure of how much light a surface reflects. Fresh snow has a very high albedo. It can reflect up to 90% of the sunlight that hits it. Dark ocean water, by contrast, absorbs most of the light that reaches it. The tundra, covered in white for most of the year, acts like a giant mirror. It sends solar energy back outward, helping to keep the planet from warming too quickly. Without those bright northern surfaces, Earth would hold more heat. This is one of the elegant balances built into the climate system. The planet regulates itself through countless small feedbacks, and the tundra is one of the most important. Its pale surface during winter and spring pushes back against the sun's energy with quiet, steady force. The tundra also shapes the way air moves across the northern hemisphere. Cold air sitting over the Arctic creates a powerful pressure system. That system drives winds that travel thousands of miles south. The jet stream, which is a fast-moving river of air high in the atmosphere, is partly steered by the temperature difference between the cold Arctic and the warmer regions below it. When the tundra is cold and stable, the jet stream tends to flow in a tight, steady band. That keeps weather patterns predictable across North America, Europe, and Asia. The tundra's temperature, in other words, influences the weather in cities that sit far from any frozen ground. The math behind this is clean and precise. A colder Arctic means a stronger temperature difference between north and south. A stronger difference means a tighter, more stable jet stream. A tighter jet stream means more regular seasons across the mid-latitudes, where most of the world's people live. The tundra is not separate from those places. It is connected to them through the invisible machinery of the atmosphere. Water plays a role here too. During the brief summer, the tundra releases enormous amounts of moisture into the air. The waterlogged plains and shallow ponds that cover so much of the Arctic surface allow water to evaporate steadily under the long summer sun. moisture rises, forms clouds, and eventually falls as rain or snow somewhere else. The tundra feeds the water cycle of the entire northern hemisphere, contributing to precipitation patterns far beyond its own borders. Scientists have calculated that the Arctic tundra and its surrounding regions influence precipitation as far south as the American Midwest and Central Europe. The moisture that rises off those cold, wet plains in July may fall as rain on a wheat field in Kansas weeks later. The distance seems impossible, but the atmosphere moves without stopping, carrying heat and water from one end of the world to the other. There is also the matter of energy balance. The tundra receives sunlight for only a short window each year. During the long polar winter, the sun barely rises above the horizon, and some regions receive no direct sunlight at all for months. The energy budget of the tundra, meaning the difference between the heat it receives and the heat it gives back, runs at a deficit for much of the year. The land loses more energy than it gains. That constant cooling effect anchors the temperature of the entire Arctic region, and through the atmosphere, the temperature of the planet as a whole. These are not small forces. They are planetary in scale, and they operate through simple, repeating rules. Light hits a surface. Some of it bounces back. Cold air sinks. Warm air rises. Water evaporates and falls again. The same physics that governs a drop of water on a window pane governs the climate of an entire hemisphere. The tundra sits at the top of the world and runs these calculations quietly. Every hour of every day, in every season. It does not announce itself. It simply does its work, and the rest of the planet, without knowing it, depends on that work being done. Beneath the tundra's surface, something extraordinary is happening. Something quiet and invisible and vast. The frozen ground holds a secret that scientists are only beginning to fully understand. Locked inside the permafrost, that deep layer of soil that never thaws, is an enormous store of carbon. Not carbon floating in the air. Carbon buried in the ground, frozen solid, held in place by the cold. This carbon did not arrive all at once. It built up slowly over thousands of years. When plants die died on the tundra, they did not fully decay. In warmer places, dead leaves and roots break down quickly. Bacteria eat them. Fungi dissolve them. The carbon inside them returns to the air as carbon dioxide. But in the tundra, the cold slows everything down. Dead plants sink into the soil and freeze before they can fully break apart. Layer by layer, season by season, the carbon piled up. Scientists estimate that the Arctic permafrost holds roughly twice as much carbon as is currently in Earth's entire atmosphere. That number is worth sitting with for a moment. Twice as much. Stored underground. Frozen in place. The tundra, in this way, acts like a vault. A cold, silent vault that has been sealed for millennia. The conditions that created this vault are precise. The temperature must stay below freezing for most of the year. The soil must remain locked and still. The permafrost must hold. Change any one of those conditions, and the vault begins to open. This is what makes the tundra's balance so delicate. It is not just a cold place. It is a system built on exact thresholds. A few degrees of warming can cross those thresholds. When the permafrost thaws, even slightly, the bacteria that were frozen inside it wake up. They begin to do what bacteria have always done. They eat the dead plant matter around them. And as they eat, they release carbon dioxide and methane into the air. Methane is a greenhouse gas, meaning it traps heat in the atmosphere. It traps heat far more efficiently than carbon dioxide does, at least in the short term. Scientists have measured methane bubbling up from thawing lakes in Siberia and Alaska. The bubbles rise through dark water and pop at the surface, releasing gas that has been locked underground since the last ice age. The planet's temperature and the tundra's frozen ground are locked in a careful relationship. The cold keeps the carbon buried. The buried carbon stays out of the atmosphere. The atmosphere stays in balance. Life on Earth, including human life, depends on that balance holding. The atmosphere is thin, far thinner than most people imagine. If you shrank the Earth to the size of an apple, the atmosphere would be no thicker than the apple's skin. That thin skin is what keeps the planet warm enough for liquid water, warm enough for life. gases inside it, including carbon dioxide and methane, act like a blanket. The right amount of blanket keeps the planet comfortable. Too much, and the heat builds. The tundra has been part of this system for a very long time. It has helped regulate the planet's temperature through ice ages and warming periods. It has absorbed carbon during cool epochs and held it in place. The fact that so much carbon is still locked underground is a sign of how stable the system has been. Stable, but not permanent. Stability is not the same as permanence. It means the forces are balanced right now. It means the conditions are holding. It does not mean they will hold forever. What is remarkable is how many things had to be exactly right for this system to exist at all. Earth's distance from the sun gives it just enough warmth for liquid water, but not so much that the poles cannot freeze. The tilt of Earth's axis creates the seasons that drive the freeze and thaw cycle. The composition of the atmosphere keeps the planet warm enough to be habitable, but cool enough to maintain polar ice. Remove any one of these factors, and the tundra, as we know, it does not exist. The carbon vault does not form. The climate engine runs differently. The tundra did not plan any of this. It simply responded to the conditions around it, the way all living systems do. Cold came, and life adapted. Carbon accumulated, and the frozen ground held it. The planet found a rhythm, and the tundra became one of its steadiest beats. That rhythm has kept the air breathable, the oceans from boiling, and the seasons turning for longer than any human civilization has existed. It is a quiet kind of power, the kind that only becomes visible when you stop and look at what it is holding in place. And yet, for all that quiet power, the tundra holds mysteries that science has not yet solved. Some of the most surprising things happening in the Arctic right now are things that researchers did not expect to find. One of them is fire. The tundra is burning, not in the way a forest burns, with tall flames climbing through dry timber. The tundra burns low and slow, creeping across the ground, consuming the peat, that thick, dark layer of ancient, compressed plant material that has been building up for thousands of years. These fires are called zombie fires by some scientists because they do not always die in winter. Evidence suggests that some of them smolder underground through the cold months, buried beneath snow, feeding on the deep peat below the frost line, and then re-emerge the following summer as if they never went out. This is not something scientists fully understand yet. The conditions that allow a fire to survive an Arctic winter, buried under ice and snow, are still being studied. Researchers know it happens. They have tracked fires that went dormant in autumn and reappeared in spring in the same location, burning from the same underground source. But the exact mechanics, how deep the fire travels, how much oxygen it needs, how long it can survive, are still open questions. The tundra is teaching us something new, and we are still learning the language. What makes this more striking is the scale. In 2019 and 2020, the Siberian tundra experienced some of the largest fires ever recorded in the Arctic. Millions of acres burned. The smoke rose so high it crossed continents. Satellites tracked the plumes drifting over the Pacific Ocean. Scientists watching from space saw something that had rarely been seen before, and they are still working to understand what it means for the carbon stored in that ancient peat. When peat burns, it releases carbon dioxide and methane that has been locked underground for centuries, sometimes thousands of years. That carbon goes back into the atmosphere in a matter of weeks. How much was released, and how much that changes the global carbon balance, is still being calculated. There is another mystery connected to these fires. The tundra is supposed to be too wet to burn easily. Peat holds enormous amounts of water. In a healthy, cold tundra, the ground stays damp enough that fire cannot take hold. But as temperatures rise, the surface dries out faster in summer. The permafrost beneath begins to thaw, and the water that once stayed locked in the ground drains away. The land becomes drier than it has been in a very long time. Scientists believe this drying is what is making fires possible in places where fires almost never occurred before. But the exact relationship between warming, drying, and fire frequency is still being mapped. The data is still coming in. Some researchers are also studying what happens to the land after a tundra fire passes through. dark, charred surface left behind absorbs more heat from the sun than the pale, reflective ground it replaced. This warming effect can accelerate the thaw of the permafrost below. The thaw releases more carbon. The carbon warms the atmosphere. The atmosphere warms the tundra. The cycle feeds itself. Scientists call this a feedback loop, a process where one change triggers another change that makes the first change worse. How fast this loop runs, and whether there are natural breaks that slow it down, is one of the most pressing open questions in climate science today. There are smaller mysteries too. Researchers have found that some burned tundra patches recover faster than expected. Certain mosses and grasses return within a few years. Some areas even show signs of increased plant growth after a fire, because the ash adds nutrients to the soil. Whether this recovery is strong enough to offset the carbon lost in the burn, nobody knows yet. The math is complicated, and the tundra does not give up its answers easily. What is clear is that the tundra is changing faster than our models predicted. The fires are one sign of that. The thawing ground is another. The shifting ranges of animals and plants are a third. Scientists are working hard to keep up, deploying sensors across the Arctic, launching satellites, drilling ice cores, and studying soil samples taken from places few people ever visit. Each piece of data adds a little more to the picture, but the picture is still forming. The tundra has existed for millions of years without anyone watching it closely. Now, for the first time, human eyes are trained on it. And what those eyes are finding is that this quiet, frozen place is full of questions we have only just begun to ask. One of those questions sits just beneath your feet if you were standing on the tundra right now. The ground there has been frozen for thousands of years. In some places, it has been frozen for hundreds of thousands of years. That frozen ground, the permafrost, holds an enormous amount of carbon locked inside it. Ancient plants died and sank into the cold soil long ago. The cold stopped them from rotting fully, so the carbon in those old plants just stayed there, frozen and still, waiting. Now the ground is warming, and when permafrost thaws, that old organic material, the remnants of plants and animals from long ago ages begins to break down at last. Microbes wake up inside the soil. They go to work on all that stored carbon. And as they do, they release carbon dioxide and methane into the air. Methane is a gas that traps heat in the atmosphere far more powerfully than carbon dioxide does. Scientists estimate that the Arctic permafrost holds roughly twice as much carbon as is currently in Earth's entire atmosphere. That is a staggering amount. The thawing is already happening across Siberia, Alaska, and northern Canada. The ground that has been solid for millennia is softening. Roads buckle. Buildings tilt. Trees in some areas lean at strange angles because the soil beneath them has lost its rigidity. Scientists call these leaning forests drunken forests, and they are spreading. The land itself is changing shape as the ice within the soil melts and the ground sinks. This sinking is called thermokarst, and it creates uneven, hummocky terrain, full of new ponds and depressions where flat ground once stood. Those new ponds matter more than they might seem. When permafrost thaws beneath a body of water, the warming speeds up. Water holds heat differently than air does. It keeps the ground beneath it warmer for longer. So a thaw pond can accelerate the very process that created it. The permafrost melts faster under the water. The pond grows, and more carbon escapes. Scientists have observed this feedback loop in real time across the Arctic. It is one of the reasons some researchers believe the tundra could shift from a carbon sink, a place that absorbs more carbon than it releases, into a carbon source, a place that releases more than it absorbs. That shift, if it happens fully, would have consequences for the entire planet's climate. But the future is not written in a single line. The tundra is complicated, and it does not move in only one direction. As temperatures rise, some areas of the tundra are seeing more plant growth. Shrubs are spreading northward. Grasses are thickening. Taller plants cast more shade and hold more moisture. In some places, this increased plant growth absorbs carbon from the air, which partially offsets what the thawing soil releases. Scientists call this process shrubification, and they are watching it closely, trying to understand whether the new growth can keep pace with the losses underground. On a longer timescale, the future of the tundra stretches into something almost unimaginable. Over thousands of years, if warming continues, much of what we call tundra today could become boreal forest. The great belt of spruce and pine trees that currently sits just to the south. The tree line, the boundary where forests give way to open tundra, is already moving northward in many regions. Trees are appearing in places where no tree has stood in recorded history. The tundra, as a biome, a distinct kind of place with its own rules and rhythms, may shrink dramatically over the coming centuries. Over millions of years, the story grows even larger. The continents will continue to drift. The Arctic Ocean may one day be positioned differently relative to the poles. Ice ages will come and go, as they always have, driven by slow wobbles in Earth's orbit around the sun. The permafrost that exists today may freeze again in some distant future age, locking new carbon away once more. The planet has done this before. It has been warmer. It has been colder. It has worn many different faces across its long life. And in 1 billion years, the sun itself will have grown brighter and hotter. The ice that defines the tundra will be gone. The Arctic will be unrecognizable, but something will still be here. Some form of life, shaped by whatever conditions exist, will have found a way. Life on this planet has survived 5 mass extinctions. It has endured asteroid strikes, volcanic winters, and the slow drift of continents. It is persistent in a way that is almost hard to believe. The tundra, as we know it, is fragile, but the story of life on Earth is not. That story keeps going, always becoming something new. For tens of thousands of years, people have called the tundra home. They did not arrive by accident. They followed the animals, the seasons, and the slow pull of survival northward. And they stayed. They built entire ways of life in one of the coldest, most demanding places on Earth. The indigenous peoples of the Arctic include many distinct groups. The Inuit live across northern Canada, Alaska, and Greenland. The Yupik people inhabit parts of Alaska and Siberia. The Sami have lived across northern Scandinavia and Russia for thousands of years, herding reindeer across the open tundra. These are not one people. They are many peoples, each with their own languages, traditions, and deep knowledge of the land they call home. That knowledge is extraordinary. The Inuit developed dozens of words to describe different kinds of snow and ice. Not because language is decorative, but because survival depended on it. Knowing the difference between ice that holds weight and ice that breaks means the difference between life and death. Knowing which direction the wind shifts before a storm gives a hunter time to return home. This is science. It is careful, tested, passed down through generations, earned through long experience with a very unforgiving world. The Sami people have herded reindeer across the tundra for at least 2,000 years. Their migrations follow the same ancient routes the animals have always walked. They read the land the way others read a map. They know which valleys hold the deepest snow, which hillsides catch the first spring growth, which rivers run clear, and which run dangerous. Their relationship with the reindeer is not just economic. It is cultural, spiritual, and deeply woven into who they are. The Yupik people of Alaska and Siberia built their lives around the sea and the tundra both. They hunted marine mammals, fished the rivers, and gathered plants from the summer tundra. Their homes were designed to hold warmth in temperatures that could kill an unprotected person in minutes. The traditional sod house, built partly underground and insulated with earth and animal skins, used the permafrost itself as a kind of natural refrigerator, keeping food preserved through the long winter. These peoples understood permafrost long before scientists gave it a name. They knew the ground beneath them was frozen deep. They knew certain places were solid and certain places were not. They knew the tundra's surface could be treacherous in spring, when the top layer thaws and the frozen ground below turns everything to mud. That knowledge shaped where they built, where they traveled, and how they lived. Now, climate change is shifting the world these communities have known for generations. The permafrost is thawing. Coastlines are eroding faster as sea ice retreats and waves strike shores that were once protected by frozen ground. Some villages in Alaska are losing land to the sea at a rate that was unimaginable just decades ago. several communities have already begun the painful process of relocating entirely. The tundra is changing faster than it has in thousands of years, and the people who know it best are watching it happen in real time. Their observations matter deeply to science. Indigenous knowledge holders have documented changes in animal behavior, ice conditions, and plant growth that match and sometimes precede what researchers find in their data. The two ways of knowing, traditional and scientific, are not in conflict. They are looking at the same world from different angles, and together they see more clearly than either could alone. Step back even further, and the picture grows quiet and vast. The atoms in a Sami herder's body were forged in stars that burned out billions of years before the Earth existed. The calcium in their bones, the iron in their blood, the oxygen they breathe on a cold Arctic morning, all of it came from the same ancient stellar fires that built every living thing on this planet. The tundra beneath their feet is made of the same matter. The reindeer they follow, the lichen the reindeer eat, the frozen soil that holds the carbon of ancient forests, all of it the same atoms, cycling endlessly through different forms. The people of the frozen north did not conquer the tundra. They became part of it. They learned its rhythms and matched their own lives to them. They are as much a part of this cold and beautiful place as the Arctic fox, the caribou, or the tiny yellow poppy pushing through the frost. And that, in the end, is what the tundra teaches most quietly. That belonging to a place means learning to listen to it. That survival comes not from fighting the cold, but from understanding it, from respecting it, from knowing deep in your bones that the land is alive and that you are part of it. The tundra holds that lesson quietly, the way it holds everything, with patience, with cold, clear stillness, with the kind of silence that asks nothing of you except that you pay attention. Right now, somewhere above the Arctic Circle, the sun is low on the horizon. It casts a long, amber light across the frozen plain. The snow glows faintly pink. The shadows stretch for miles. A single Arctic fox trots across the open ground, its white coat blending into the white world around it. It does not hurry. It moves the way the tundra moves, slowly, steadily, with a kind of quiet confidence that comes from knowing this place completely. This is the tundra at the edge of tomorrow, and it is still here. It has been here for thousands of years, long before the first human being walked across the Bering Land Bridge and looked out at the frozen plain ahead, long before the first caribou herd found its migration path, long before the first willow tree learned to grow flat against the ground to escape the wind. The tundra was already old when all of that began. It had already survived ice ages and warming periods. It had already watched glaciers advance and retreat. It had already stored in its frozen soil the memory of forests that lived and died long before our species existed. And through all of that, it kept going. It kept cycling. Carbon in, carbon out. Snow falling, snow melting. Animals arriving in summer, vanishing in winter. The permafrost holding steady beneath it, all like a slow, cold heartbeat. Scientists who study the tundra today describe it as one of the most sensitive places on Earth. Sensitive, in this case, means responsive. It means the tundra notices change quickly. It means that small shifts in temperature produce large shifts in the land. The permafrost that took thousands of years to form can begin to thaw in a single human lifetime. The frozen carbon it holds, locked away for millennia, can begin to release. The land itself can soften and sink. These are real and serious changes. The people who live there see them. The animals feel them. The scientists measure them carefully, year by year, watching the numbers shift. But the tundra is also resilient. That word means it can recover, that it has a kind of deep strength built from long endurance. It has survived before. It has changed before. Life has found ways to persist in this place through conditions that would seem impossible from the outside. Tiny plants pushing through frost. Bears sleeping through months of darkness. Birds flying from one end of the earth to the other just to spend a few weeks on this frozen plain. The tundra does not give up. It adapts. It waits. It finds a way. And we are part of that story now. Every person on Earth is connected to the tundra, whether they have ever seen it or not. The carbon it stores affects the air we breathe. The ice it holds affects the oceans we depend on. The animals that move through it are part of food webs that stretch far beyond the Arctic. What happens in the tundra does not stay in the tundra. It moves outward, the way everything in nature moves, in slow, wide circles that eventually touch everything else. That is the quiet truth this episode has been building toward, fact by fact, image by image. The tundra is not separate from the rest of the world. It is woven into it. The frozen soil and the tropical rainforest are part of the same system. The Arctic fox and the deep-sea fish breathe air shaped by the same planetary forces. The lichen on a tundra rock and the coral on a reef are both doing the slow, patient work of turning sunlight and minerals into life. Everything is connected. Everything is cycling. Everything is part of one long, unbroken process that began with the formation of this planet and has not stopped since. Right now, the Earth is spinning. It has been spinning for 4.5 billion years without stopping. The tundra is turning slowly through the dark, under a sky full of stars. The permafrost is holding. The Arctic fox is curled in the snow, its tail wrapped around its nose, its small body warm inside its thick winter coat. The caribou are somewhere on the plain, breathing slow clouds of steam into the cold air. The planet is at rest, and so, gently, are you. The tundra will still be there tomorrow, patient, cold, and full of quiet wonder. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.